Swayam Prabha. Digital India. Educated India.
Welcome to Introduction to Machine Learning. In today's lecture, we will go through the overview of machine learning and set up the context for the course. So this lecture will be less from an engineering perspective, less from the practitioner's perspective, but more from a general knowledge or a managerial perspective about things to keep in mind when you think about machine learning, and see how the rest of the course fits in with the broader use and practice of machine learning. So the questions that we will answer in this lecture will be: is machine learning a fad? What is machine learning? How is it related to artificial intelligence, neural networks and deep learning? What makes a problem a good problem or not so good problem for machine learning? And how should one critique machine learning models that may be presented to someone? What questions should be asked about the performance of machine learning beyond just accuracies and so forth? And what are some of the myths and realities related to machine learning? So let's first talk about whether AI, ML or artificial intelligence and machine learning is a fad. So every few years we hear about some technology that many people get excited about. So for example, nanotechnology was quite a hot topic a couple of years ago. Similarly, these days machine learning is a hot topic. So there was a lot of investment that flows into that hot topic from funding agencies, research funding agencies, as well as industry and so forth. But not everything is a fad. Some of these do lead to useful technology. So for example, from the IT fad that was there 20 years ago, all our computer and network infrastructure that we take for granted, such as online shopping, online banking, etc., that came into being. There have been examples of successful applications of nanotechnology in drug delivery and so forth also. And some of these have deeply affected our lives, and they have become so integrated with our economy and society, and they have reached a level of maturity from the point of view of ongoing innovation, that we don't see too much of ongoing innovation, because the innovations, the foundations of that was already laid 10-20 years ago, and now these have become so seamlessly integrated that we don't talk about them as much. So that doesn't mean that these were fads that just faded away, but obviously with every new technology there is some overexcitement also, and not all of that pans out. Some of it yields useful results to varying degrees, depending on the technology, depending on the challenges, and depending on the use cases that people find from that. So as we start working on these technologies, the challenges become clear to us, and then we realize that not everything is there to revolutionize the world, but it can revolutionize parts of the world. So we have come across in different business case studies, etc., we come across a chart like this that tells you what is a technology cycle. So as time progresses, let me use my laser pointer, as time progresses and we look at the value or the investment in a particular technology, when it starts to go up, we are in the innovation phase, then we reach a maturity phase, and then we reach a decline phase. So the decline usually can be because of two reasons or a mix of reasons, but the main two reasons are that the challenges in actually operationalizing certain technology become clear to us, and because of that, that initial hype dies out, or the innovations have already taken place during the maturity or even the innovation phase, and now it has become a commodity, and because of that there's a decline in actually further innovation, but more about using the technology. Plus, not all cycles are the way you see on this particular chart. There are other ways in which the technology matures. So for example, it not only becomes a commodity, but there could be double humps in the investment that goes on into a technology, and that is because after we have realized the challenges here and there's a decline in its in the investment in that technology, there can be other breakthroughs that lead to a new wave of innovation, and that I believe is what is happening with machine learning. And this new wave of innovation is coming from several factors that we'll look at shortly. So machine learning is already being deeply embedded into our economy and society. We take it for granted in many of the applications that we use, especially on the web and on our mobile phones. So for example, face recognition or face verification is now quite a ubiquitous technology on social media. So if you put up your images on Facebook, Facebook matches it with your old images and gives you an automatic tag that this is this person, this is that person, and this is you. Would you like to tag these people in the photographs? So that is already there, at least for the entertainment purpose, and it is also being used in several critical areas such as in industry for defect detection and so forth, in military and intelligence for recognizing people in crowds and so forth, specific peoples of interest, and also in automated reading of bank checks. When you handwrite a check, not all these checks go through a human human reading, they go through machine reading. A lot of them go through machine reading. Automatic extraction of images from IDs and so forth. So all these innovations are already being making our lives more convenient, making processes, business processes more efficient and so forth. Then similarly, advances are taking place in voice and so voice to text conversion, machine translation, etc. So you will see now when you watch videos on certain platforms such as YouTube, you can turn on automatic captioning, and none of those have been marked by humans. They are recognizing the speech based on the audio signal itself, which is driven by machine learning. It's impossible to actually write a program from hand to convert speech signals into automatic text. Then several companies are going towards chatbot based customer service, where they have a repository of answers that questions and answers that that are relevant to their customers, and now you can type your question in a slightly different way than what has been there in the repository, and machine learning based engines will process your text and they will match it to the nearest query that they have in that database and give you the relevant answer. And then you can, if you give feedback that whether you are satisfied with the answer or not satisfied with the answer, that feedback itself goes into the next version of that chatbot to make it better over time. Similarly, a lot of trading on stock exchanges now has become automated and based on algorithms, and a large subsection of those algorithms, sub part of those algorithms, they are now using machine learning. We are going more and more towards automated decision making. So there is a lot of research going on in automated driving, so self-driving cars, and automated UAVs that will at least be able to navigate to the point of interest, and then the operator can take over for the specific task that is to be done at that point. And also in medical diagnosis, criminal forensics and so forth. So in a nutshell, what is machine learning and what is, so there are two phases of machine learning. One is called training and the other is called deployment. And basically what we do in the training phase is that we take a lot of data, we'll take a lot of input data, and if I talk specifically about supervised machine learning, it will be paired with labels. So an example would be, this is my face and then the label is my name, and I could have 1,000 other faces and they will have their own labels. Some of those could also be my other images, but some of those could be other people and not my images, and so forth. So each input, in this example an image, or in a speech to text it could be an audio signal, and the label could be the actual text that has to be derived from that audio signal. So each input is paired with a label, and that's where most of the recent advances in machine learning have come, is in supervised machine learning, where each input is labeled with each input is paired with a label. So once we have these labels and we have a large data set of these labels, the machine learning algorithm basically figures out a model, and this model basically learns to map inputs to the correct labels. And it is only useful if we can take future inputs and pair it now with the model instead of the labels, and the model computes the label. And if we have more and more labels that are correctly labeled, that is going to make the labeling process more efficient, more automated, and more time saving. So we have two distinct phases in machine learning. One is training on past data, and then the next one is deployment or inference or testing, which is basically prediction on future data. So only when we are making correct predictions, useful predictions, we have a useful machine learning model, and its utility is based on figuring out good problems to solve, figuring out good models or structure of the models, frameworks for the models that can be used for this particular problem, whichever problem that you are working on. So we hear a lot of these words: artificial intelligence, machine learning, neural networks, deep learning. So how are they all related to each other? Artificial intelligence is a very broad term. Whenever we think that a machine is behaving in a non-trivial manner, its algorithm you cannot describe in words simply, then it is artificial intelligence. But that could be anything, right? So one classical definition of artificial intelligence was given by Alan Turing, which was the Turing test, that if you can give a machine some written text and the machine gives you some written text back, and you are not able to distinguish between whether the text that was sent back to you was written by a human or by a machine, then the machine is intelligent. So that's one way of looking at it. Now we can extend this to other fields. If I give a machine an image and the machine labels the image and gives it back to me, and I'm not able to distinguish whether the image was labeled by a machine or a human, then perhaps that machine is also intelligent. And same thing can be said about several other problems. So that is one way of measuring intelligence, where we are holding ourselves, human intelligence, as a gold standard, and we are seeing whether machines can do the same job indistinguishably from humans. So but that can be accomplished in many ways. We can have a complex algorithm, a lot of rules that are written by hand, which is what all the research in expert systems was about some 40 years ago, where the goal was to write a complicated set of rules and decision flow, so that the decisions that are made, they seem intelligent, or basically they achieve a useful purpose, but they are complex and then they seem non-trivial. An example of a trivial decision would be that predict where the moon will be 24 hours from now, based on physics of how the moon moves, how the earth moves, and how they interact with some of the nearer planets and so forth. It's probably we can write a formula. It might be a slightly long formula, it might take a whole page to write that formula, but we can write the formula to predict where the moon will be 24 hours from now, given its position today, and so forth. So that is not so much of an not so much an evidence of artificial intelligence, that particular formula, if you are just putting the date and time and it is predicting where the moon will be or what will be the phase of the moon and so forth, because it's quite a deterministic formula, and we can explain it to, we can write it in the parlance of, let's say, high school mathematics. On the other hand, there are several intelligent behavior where we cannot figure that formula out, even if it is very complex. We cannot write it by hand. What is required is we require a lot of samples of what is the input and what is the desired output, and based on that we write a meta algorithm that to figure out the algorithm from going from the input to the output. So whenever we require a lot of training data and the behavior depends on the training data, then we are in machine learning realm, which is a subset of artificial intelligence, so to speak. So these machines could be, they behave as if they are behaving intelligently, but their underlying algorithm is based on training data. Within machine learning, there is a specific framework of machine learning algorithms which are called neural networks. These are layered formulas in some sense, and they are built up of simple units, and when all these units put together they behave intelligently, then or they model something, a complex model in a layered manner where each layer and the component of each layer is simple, then it's a neural network. So it was inspired from the human brain, which is made up of simple neurons, but when many of them are put together, the neurons and their connections actually hold vast knowledge and our whole essence of being, thinking, philosophizing, etc. So within neural networks there are specific types of neural networks which are deep, they have many layers, or they propagate their signal through several neurons, several layers of neurons. Those are called deep learning neural networks or deep neural networks. These type of neural networks in the last 10 years have become quite prominent in various applications, and there are specific reasons why they have become so useful today. I will come to those reasons shortly. So why is it that we are seeing a lot of use of machine learning, a lot of buzz around machine learning, a lot of investment in machine learning, a lot of desire to learn machine learning and so forth? Several things, several phenomena have come together to there's a confluence of these things together that we are seeing that. First of all, we have lots of data. So machine learning, because it learns from data, we have a lot of data to train on. We have inexpensive ways of collecting, storing and transmitting data today based on the internet, based on cheap memories, cheap disks and so forth, and also cheap sensors to collect data. So because of that, so like if you think about your cell phone, which may cost a few thousand rupees or a few tens or few hundreds of dollars, within that there is a very good camera which we could not have had easily access to, let's say 10-15 years ago, and that camera is a very inexpensive component of the entire cell phone system that you have, because it is mass produced and it is very small, yet it has very good optics and sensors and so forth. So the collection of data has become quite inexpensive, same with storage and transmission. The second thing that is affecting this ML revolution, enabling the ML revolution, is that the computing power, the per unit price of, let's say, a floating point operation has become quite inexpensive now. We have now cell phones that have as much compute power as some of the larger computers did 15 years ago and so forth. There are lots of server farms that you can rent on various cloud services. You can buy GPUs for a few hundred to a few $1,000s that can do a lot of parallel processing that was not imaginable even like 2 decades or 1 decade ago. And this has enabled a lot of new frameworks and algorithms that can use a lot of these data in what are known as deep learning or deep neural networks, such as the ResNet framework for image recognition and the GPT framework for processing text. So all of these things have come together to basically increase the feasibility of developing utilities that use machine learning and making our lives more efficient, our work more efficient and our lives more convenient. Thank you. So now let's see whether this machine learning is a silver bullet or not. So not all problems can be solved using machine learning, right? So when we don't know what the desired output looks like for a given input, then we might be tempted to use unsupervised machine learning. Unsupervised machine learning, unfortunately, is something where there hasn't been a whole lot of advances. There are attempts being made to work with unsupervised learning, so without having to label all the data, but those are coming, I mean, they still use learnings from supervised machine learning to actually work in unsupervised machine learning in something called self-supervised learning. True unsupervised learning, where you have no clue what you are looking for, is something that where machine learning is not very useful. When you have too little data, then also machine learning does not work very well. It does not generalize to domains where we have very little data or very little labeled data. When the data is too unstructured, then also machine learning has not been very successful. The widely used machine learning frameworks, specifically deep learning, they exploit structures in the data. So for example, in images you have a structure of pixels, left and right, top to bottom. There is a way in which pixels, neighboring pixels appear relative to their other pixels. The pixels are not random, otherwise images would look like noise. Same with audio signals. The pressure wave samples that you have in the audio signal, they are not random. There is a particular structure to that, and that is what is exploited by deep learning algorithms. Same with text. Natural language text is not just a bunch of words thrown together. There is structure of language, different types of clauses, different grammar rules, different vocabulary rules, etc. that basically allow us to construct intelligible sentences. So that those structures are important. If your data does not have that kind of structure, or you have too little data, or the data is not labeled, then machine learning is not very useful. If the model is too simple, underlying model is too simple, so for example trajectory of the moon, then it's better to use models of mathematics and physics to describe and make predictions than to use machine learning. A machine learning method to predict the trajectory of the moon would take a good number of samples, which in simpler mathematics, in a mathematical or a physical model, you would probably require 4 or 5 samples to be able to predict the trajectory of the moon. And whenever explainability is desired, then machine learning is not good. What that means is that because the machine learning models have become very complex, the only way we can test them is to put them on new data and see whether they are making good predictions on that, where we know what the prediction should have been. So that is called testing. But there is no provability. You cannot prove that it will make good decisions going forward. There is only so much confidence that we can derive because it did well on this data. It is likely to do well on a similar data, and it is just likely that I can say. I cannot say it is guaranteed to do well on new data. So that is one part of it. The other part of it is that because these machine learning models have become very complex, we cannot explain how they are making their decisions anymore. It's very difficult to explain that. We don't know what if we have 10 million parameters in a neural network, what changing one parameter would mean, what deleting one parameter would mean, other than empirically testing it out. So the sweet spot for machine learning is that we have a lot of structured data. Explainability is not critical, right? We only want to predict. So prediction accuracy is a primary goal, not explainability. And the underlying model is complex but stationary. So complex means it is not simple that you can derive it from physics, but it is also stationary in the sense that the model does not change over time. An example of a non-stationary model would be that, let's say you want to take a picture of someone's clothing and predict their age. So what seems like appropriate clothes for 60-year-olds today could have been the clothes of younger people 30 years back, and so forth. So it's not a stationary model, it changes at least slowly over time. So in those cases, machine learning models will not be able to make predictions if the underlying model itself of how the data is generated itself has changed. So it makes complex predictions, but where the relationships are rather stationary between training and testing time. So now let's talk about what do we mean by structure in the data. So the simplest of structures is that your each sample on which we want to make a prediction is a record. So what I mean by record is that you have each row is a record and it has fields. The fields are the columns. So for the first record we have the price, the margin and the volume. For the second record also we have the price and the margin and the volume. So these kinds of data are there in several applications, these will be available, and for these kinds of data basically we have these different fields that become different dimensions of the data itself, and machine learning is very good at exploiting treating these dimensions and finding relations between these dimensions appropriately to find to make good predictions about the data. So for example, let's say we want to predict volume based on price and margin and style of clothing and so forth, and season and so forth. So that could be a problem for machine learning based on past data of what has sold in a particular season at a particular price point and a particular margin and so forth. Another kind of structure in the data could be temporal order. So if you look at pressure waves for sound, there is a temporal order. I cannot take a sample here and a sample here, and I cannot just exchange them. Whereas here, if I in the record type data, if I switch these two columns, I'm not changing the nature of the data. But that's not the case in data that comes with temporal order. I cannot simply switch the fifth and the 100th sample in audio samples, because there is a particular continuity in the variation of pressure that makes it a wave with a particular frequency that helps us understand the phonemes that the person is speaking, etc. So that order has to be maintained. Similarly, in images we have a spatial order, we have a left to right and top to bottom order. We cannot randomly shuffle these pixels. Even if we shuffle all the pixels the same way across images, even then we will lose the meaning of the images, because their order determines the edges, the dark portions, the lighter portions and so forth. So the shapes that we see in images, they are quite dictated by the order of the pixels. So the order has to be maintained, and if we use machine learning frameworks that exploit that order, we are likely to get better answers, more predictive models and so forth. Similarly, another type of relationship is a web of relationships where each sample or each entity is a vertex, like a circle that is shown here, and its relationship with other entities is shown as edges, which are these lines that you see. An example would be that we model social media as graphs. So these are called graphs, where each person is a vertex, and whether or not they comment on each other's posts or like each other's posts, etc., could be the relationship that is shown in edges. This can be useful to determine communities or subgroups of people within social media. Another example could be molecules. Atoms could be the vertices, whereas how these atoms bind together, how far they are from each other, what kind of a bond, covalent or ionic bond they share, how many electrons are there in that bond, etc. Those could be the part of the edge information between these vertices. So you can have machine learning models that specifically are well tailored to exploit the graph structure of the underlying data. So these are some examples of ideal and non-ideal problems for machine learning. In ideal examples, we have image recognition type problems, such as recognize a person, thing or place in photographs, recreate speech from just lip movements, assuming we have a lot of paired videos and audios of people speaking, divide music into genres and recommend based on past likes of a person, learn inverse problems. So inverse problems are a special class of problems that are difficult to solve, but they can be a utility of using machine learning. In inverse problems, we have a forward model and an inverse model. The forward model is usually easy. In forward model, you start from something that has more information and you degrade it to get something that has less information. Now in the inverse model, we have to go from that the data with less information to data with more information. So we have to cook up information, we have to create information, but it's not as bad as it sounds, because let's take the example of images. So let's say you have a large image, and degradation means reducing the size of the image. So this is going from high resolution to low resolution, and now we want to come back from, given a low resolution image, what is the high resolution image. Obviously when we go from high resolution to low resolution, we are going to lose details. So for example, some fine drawing or some fine writing or some fine features of someone's face, those will be averaged out with other things in their surrounding, and those details will be lost. But when we recreate the larger image from the smaller image, the high resolution image, it's not that difficult. It is, there is a lot of ambiguity that can come in, that whether I should create the fine details this way or that way. But if we have seen enough of images, we can actually have a statistical model that creates plausible images, and that is where machine learning is also being used. So you synthetically go from high fidelity to low fidelity, create thousands of such paired examples, and then use a machine learning technique or machine learning framework to train on this synthetically created low fidelity data to recreate the high fidelity data, and hope that it works for actual low fidelity data also to create plausible looking high fidelity data. Then predict properties of molecules. If you have a database of molecules, you model molecules as graphs, you learn how to predict its properties such as toxicity, whether it is basic or acidic, etc., from those molecular structures, and then you try to predict that for new molecules whose properties have not been discovered, or these are molecules that are only in silico in the lab, and try to predict their properties before you actually synthesize them physically. So non-ideal problems are problems that are too simple, where physics would be a physical model would be a better predictor of the future. So for example, predicting the next solar eclipse is a problem in which principles of physics are probably much more useful than machine learning. If you don't have a whole lot of data, so for example, if you want to make a chatbot for an under-documented language, such as some tribal language that has not been documented very well, only a few thousand speakers can actually speak the language and so forth, then it will be very difficult to create a chatbot for that language. Where the models are not stationary, where the underlying working of the world is not stationary, such as predicting the next unicorn in economy, is very difficult for machine learning, because the state of the economy, the desires of the people, the wants of the people, the needs of the people keep changing, the laws of the economy keep changing, so it's very difficult to predict which company is going to be the next unicorn. Then if the problem is not very specific, so for example, develop a comprehensive system to replace doctors in diagnosis, that is very difficult to do, because all the medical problems, including rare problems, including problems that affect only certain socioeconomic class of people or certain ethnicities and so forth, all of these cannot be actually put together into a single model that can be captured and done using machine learning. Then just for fun, I put this here: you cannot predict when you will have the next fight with your spouse, because there isn't enough data, hopefully, to predict that, and hopefully humans are complex, their emotions are complex to be able to predict that and capture that in a model. So model choice becomes very critical when you are dealing with machine learning, and its rigorous validation is also very important. So what I mean by that is that you can actually have more complex models that can fit better and better on your training data, right? But that does not mean that it is always a good choice. So when you increase the model complexity, your error on the training data will keep going down. But at some point what will happen is that if we also take held out data, validation data, on which we did not train the model but we keep monitoring how it is doing on that model, we will see that at some point the error stops decreasing and it actually starts increasing if we make the model more complex. So this is probably one of the most important graphs, cartoon graphs in machine learning, that there is a sweet spot in model complexity. Models should not be more complex or less complex than that sweet spot. If they are more complex, they are overfitting. If they are less complex, they are underfitting. The only way to know overfitting is to see that whether there is a gap between training and validation error or not, and whether that gap is widening or not. There will always be some gap, and even in the sweet spot there will be a gap, but in the sweet spot we can see that the validation error is not going further down if we make the model more complex. In the underfitting area, we will never know whether it is underfitting unless we make the model more complex and at least reach some region of overfitting and then compare the two. So what does model complexity mean? So basically it means a more complex formula that is in the underlying model. So modern machine learning models are basically mathematical functions with thousands of inputs and in millions of parameters that need to be trained, that need to be determined. And increasing complexity means you can increase the number of inputs or increase the number of the training parameters. Mostly it means increasing the number of training parameters, the learnable parameters that you have in the model. To give you a more concrete example, you have, let's say we want to predict y, and we have a simple model which is w1 x1 plus w0. This is equation of a line. Here we have a single input which is x1, and we have two unknowns which is w1 and w0. So every pair of x1 and y, if we take several training examples, we will be able to fit a line, that is we will be able to determine what is w1 and w0. Now I can add another input like x2 and the model becomes slightly more complex, it has more inputs and more unknowns. And then I can also add more nonlinear functions. I can add more unknowns by introducing nonlinear terms such as x1 square, x2 square, etc., or even x1, x2. So the way, if I start making more and more, introducing more and more nonlinear terms, more and more interaction terms, then basically I'm making the model more complex. So that is what I mean by increasing model complexity. So the progress that machine learning and specifically deep learning has made in recent years has been remarkable. There used to be an annual challenge to recognize images from one of 1,000 classes. So these classes were everyday objects such as a car or a truck, and also animals such as cat, dog, horse, etc. And the training data set was quite large, million images plus, and the performance on the held out images, on the test images, was measured, and the accuracy was the competing metric for several techniques, or trying to bin the given image into its class should be among the top 5 classes out of the 1,000 classes predicted, used to be the metric. And for this competition, ever since the advent of deep learning, the accuracy of machine learning started to come closer and closer to human accuracy, and around 2015 it even exceeded human accuracy. So what does it mean to exceed human accuracy? Is basically when a single human basically identifies the object in the image, they tend to make some errors because these images were labeled by either experts or people who actually knew what the source of the image was. So imagine you are taking image of a dog but from a top angle, then from top angle when the telltale nose and eyes of the dog are not visible, then it looks like any other animal such as a cat or a goat, and there can be some confusion as to what is the class of this animal. So even humans make mistakes on this data, they are not 100% accurate. Similarly, machines are also not 100% accurate, but they are coming closer to humans. In fact, they have exceeded humans in this particular task. So when the task is very well defined, machine learning can even do better than human accuracy in those tasks, provided the gold standard for training the machine learning is already better than a single human. So that is something to keep in mind, that machine learning will not be able to exceed a certain accuracy if the gold standard itself is not very accurate. So other considerations in machine learning besides accuracy are that what is the memory footprint while training for the algorithm, while using the algorithm in inference, in testing. What is the transferability of that algorithm? That means that if you train the algorithm on dataset A, is there something that you can use in that model, in that algorithm, that will also be applicable to dataset B? Then what is the computing and power requirements for training and running the algorithm? So if you are running the model, the machine learning model on an edge device such as a cell phone, then the power requirements are much different than, let's say, if you are allowed to use a GPU server farm, then the power requirements are quite different. Then of course speed and parallelizability, how fast the algorithm learns, and can its training and inference be parallelized among different processors. So when we think about machine learning, although this course will specifically deal with training of models and testing of models, or training of algorithms and testing of algorithms, there is a lot more to machine learning than that. There is an entire life cycle of a machine learning model, and let's look at it so that we get the context of where the course will operate, but there are other considerations that we should keep in mind. So for example, the first stage of a life cycle would be needs identification. So we first need to figure out what is the economic or the social problem that we are trying to solve, and does it really require a machine learning solution or not. Like I mentioned before, several problems are either too ill-defined, or the data is not there, or the data is not structured to be amenable to machine learning, to be conducive to be solved by machine learning, or it is possible that the problem is too complicated, or it is too simple. In both cases, perhaps machine learning is not to be used too much. So that need identification as to before diving into machine learning, that is quite important. So once we have identified the need, the next stage would be data gathering. So what data is relevant to making this prediction? Is this prediction actually going to be useful? That is already taken care of in the needs identification, but now we are talking about what will help make that prediction. Is it feasible to collect that data? Is it ethical to collect that data? And is that data relevant to the problem that we are trying to solve? So that data gathering stage will be the next one. Are there biases in the data? Is it easy to collect data on males than on females, but the application of this algorithm is equally applicable to females, which means that we might be disadvantaging females with respect to this algorithm. So those kind of ethical questions, those kind of questions of bias, those questions of feasibility, is it if the data collection is too expensive, or the data collection is takes us to the other side of a ethical boundary, those are the considerations that we will have when we will be thinking about data gathering. Once we have gathered the data, then what kind of a model, machine learning model, will exploit the data dependencies within the data itself, and that is basically where most of the rest of this course will operate. So basically we will see which kind of data is suited to what kind of model. Okay, and after that, once we have done made our choice of model, or multiple models to compare, then we will be doing rigorous training and validation. So here the points to keep in mind is that when we are validating, this should be data that we have not touched when we are training the algorithm. So if we touch the data, in the sense that if we anyway use information from the validation data in the training method, then there is a chance of a data leak, and we will get over optimistic results when we validate on this particular data. And try not to hack the validation accuracy by using the validation data again and again and testing multiple models. It should be used sparingly, and in ideal case it should be one subset of that validation data, specifically called test data, should be used only once to get a good estimate of how the model performs. So after that, once your model is ready, then it has to be deployed, where it will be working on real data on that it has not seen before. And during deployment, we need to make sure that the person who's using the model, they are very well aware of what was the intent of the model, what kind of data it was trained on, and what kind of data it was not trained or validated on. That is important, because then they will be cognizant of potential biases that the algorithm or the model might have while applying it in a new situation during deployment. So that has to be kept in mind. And an often overlooked part of the entire machine learning cycle is the monitoring of the models. So once it has been deployed, it is not fire and forget, in the sense that deploy and forget. We also need to monitor whether whether new biases are creeping in, because the data in the deployment scenario is different from the data that was used in the data gathering scenario, because we did not anticipate a certain type of use case or a certain type of demographics or a certain kind of data distribution at the deployment stage. And then there could also be something called concept drift, that we anticipated the kind of data that that it will be used on, but now somehow the data characteristics are changing. So for example, the sensors could be failing, or the sensors could be replaced by even better sensors. That could also lead to problems. Or for example, let's say we are looking at people, but the people are aging, or the people's fashions are changing, their preferences are changing, and so forth. So all these have to be kept in mind while we are monitoring the use of the machine learning. So when we are thinking about like ethics of machine learning, we have to also think about each of these stages and some human responsibility at each of these stages. At no stage we can say that, okay, now it is AI is like its own being and it is responsible for itself. That is never going to be the case. It's basically a tool that is being used in different scenarios. So some human has to be responsible for the handoff for that stage and the handoff to the next stage, and receiving from the previous stage. So anytime the algorithm doesn't work in any particular stage, we have to retrace our steps back and start from one of the previous stages, and then retrace all the steps back. You cannot skip steps going forward. Okay. So what we will do in this course, we will mostly concentrate on model choice, training and validation, but all these other things are also in the context of machine learning, they have to be kept in mind. So they are often overlooked questions that straightforward, they flow from that life cycle. So basically, did we find the right problem or the societal need to solve? Does it require a machine learning solution? And then data and its provenance. So did we use relevant and enough data? Was the data diverse and representative of the deployment scenario? Are we disadvantaging certain, let's say, subgroups of people, even though economically they may not be important, but ethically it may be important to make sure that there are no biases that creep into the model. Do we have, is the data ethically gathered and stored? Did we have enough security measures so that the data is not given to people, is not accessible by someone who's not authorized to look at the data? So ethics also, to give you a strong example of ethically collected data is, if you are building machine learning for medical applications, there is a concept of consenting to give our data, and there is also a concept of waiver of consent. When the data is de-identified and the person cannot be identified from the data, then in certain cases for research, if the consent originally was not taken, that waiver of consent can be given, as long as there is no risk of identifying the person whose data is being used, and whether the data was meticulously recorded. So these are some of the things that we have to worry about while looking at building machine learning models. And then of course we also look at the model. Does it exploit the structure of the data? Is it sufficiently complex? Is it too complex, right? And is it not complex enough for the given data. So if you have a million data points and only 5 dimensions, right, so there are you can have actually models that are too complicated. If you have several dimensions instead of 5 dimensions, you have let's say a 100 by 100 image, which is like 10,000 dimensions. In that case, you want models to be complex enough, and you want models that will exploit the structure of the data, such as a convolutional neural network in this particular case. And does it meet the deployment constraint? So your training situation, the training hardware and infrastructure can be very different from the hardware infrastructure on which the model will be deployed. So having a more accurate, more robust, and a large, sufficiently complex model is not always a good thing, because the deployment scenario may not be able to absorb and use that model. Then when we validate the model, did we use a realistic scenario instead of using too optimistic a scenario? Did we try to ignore all the boundary cases where the model fails and explain it to ourselves that these will not occur in the test scenario, or we will caution the user that not to let this kind of data be tested on the model? So these are all different ways in which biases and too much optimism can creep in while validating a model. Did we cover the diversity of use cases on which in which the model will be used, and are the performance metrics even meaningful? So to give you an example, if 99% of the people don't have cancer and 1% of the people have cancer in a given population, and we build a cancer detector and it says no one has cancer, then obviously the model is not good. But if we just compute accuracy, that's going to be 99%. So the accuracy by itself is not a good metric. There are some better metrics, such as area under curve, or F1 score and so forth, or looking at two metrics simultaneously, like sensitivity and specificity. So all those have to be kept in mind while we are validating a particular model. And then, did we give enough user guidance on people who are using the model to declare the use case on which it was intended, and the description of the data on which it was trained and validated? Then once the model is performing in the field, then we have to monitor the in-field performance to see whether there are any data differences and concept drifts that are coming into the model, and also unauthorized or unethical uses of the particular model. So let's say if we build a model which recognizes emotion based on faces, but it is meant only for entertainment purposes. So it is only for basically putting some kind of face filters based on your emotions, or some kind of emojis based on your emotions. But let's say someone uses that for interrogating a suspect, and we know that this is not that rigorously tested to incriminate anyone who's being interrogated for a legal issue, then that's an unauthorized and an unethical use of that particular model. So I will give you a few situations in which we can ask different critical questions about the statements that are made about different machine learning models based on the discussion that we have had so far. So let's say if someone comes and says that we need to store every keystroke and mouse movement of how our employees use the computers, so that we can run machine learning on it later. So let's pause for a bit and think about what are the critical questions we can ask in such a scenario. So obviously, if someone is very zealous about using machine learning, they would love to have this data to do various kinds of analytics on it later on. But is it even ethical to store every keystroke of your employee? Number one. Number two, what is the data requirement, the storage requirement of storing such a large data? Number three, the question about what you want to do with it is not defined. So all these are like different critical questions that can be asked for a scenario like this. Then let's say someone comes and says that our product can give biometric access based on face recognition, no need for cumbersome finger IDs, finger scans, IDs, or iris scans. So what will you ask that person? So the question would be not just accuracy, but also asking them about accuracy under what scenario. What if the background in which the face is taken, face image is taken, if that changes? What if the lighting changes? What if the faces are of a different ethnicity or a religious group? So for example, Sikhs will have unshaven faces in many cases. So does it work on unshaven faces? Or if you go to certain countries where a certain kind of a headscarf is the norm, then does the algorithm perform well on that also? Was it only trained on certain ethnicity and then you are using it for faces of a different ethnicity? Was it tested on that, and so forth? Then this one is easy. This is an example I talked about a few minutes ago. If someone says that we can detect pneumonia in chest x-ray with 99% accuracy, the next question would be, what does 99% accuracy mean? What was your sample population? What was the breakup of pneumonia versus non-pneumonia in the sample population on which it was tested? And instead of accuracy, can you tell me area under the curve, or F1 score, or sensitivity with specificity, etc. So these are like different ways of probing such a claim that we have a 99% accuracy in detecting some medical condition. This again is another example that we have discussed before. We can recognize people's emotions with 91% accuracy from their faces as they watch videos on our website. So several relevant questions that can be asked are what is the base emotion, and how likely is the base emotion? It could be a neutral face, for example, and that itself could be like more than 90% of the times. Then is 91% accuracy even good? Second question is, did we take the person's consent before recording and giving them doing the analysis on their faces, etc. And then does it work on different backgrounds, different ethnicities, etc., etc. And similarly, if someone says our video call plugin can tell when people are lying, so again the question arises is that how accurate is it? Did you say that it is for an entertainment purpose only, or does it work on different ethnicities and backgrounds and so forth? Our autonomous vehicle is 20 times safer than an average driver. Now this average driver is under which condition? Is it on during highway driving? Is it in less crowded highways or less crowded streets? Is it adaptable to more chaotic driving, such as what we are familiar with in India, for example? Is it familiar with a different type of traffic mix, and so forth? And then we can also ask another ethical question: if indeed a self-driving technology is 20 times safer than an average driver, then is it ethical to let the average driver drive? So with all this in mind, let's look at which directions machine learning research is going in. A lot of the work, in spite of these advances, has been in basically trying to reduce the data that is required for training for a new scenario. So there is a lot of research going on in training with unlabeled data, training with fewer data sample. So unlabeled data, the most important example of the type of techniques that are being used is something called self-supervised. So this is still supervised learning, but the underlying task for training is created from the data itself. You don't need extra labeling for it. Training with fewer labels, this is called few shot learning. And then training with high level data labeling, this is called weakly supervised. So you don't give data for each and every sample, but you give it for let's say a group of samples. Learning from one task and taking the learning to another task, this is transfer learning. Design models that can explain their decision, this is explainable AI. This is there has not been much of a usable advances in this, but there is a vigorous research that is going on in making AI more explainable. and make AI more cautious to new scenarios. So this is basically calibrated AI. So the AI should not be forced. So currently the way AI is trained or machine learning is trained is that given the categories on which it is trained, it is forced to give a decision on one of those categories, but it should also be able to recognize that the data is something that is ambiguous and it is not able to make a decision, calibrated. So it is calibrated to know its own uncertainty. One more thing that I will add here is federated learning. So what is federated learning is that let's say there are two data sets and combining both data sets will give a better model, but the two data sets are held by two different organizations and they don't want to share the data per se, but they want to collaborate on training a model. So how can we train a model that basically does not reveal data of organization A to organization B and vice versa, yet it can benefit from both of these models. So that is federated learning. So that is another topic of interest today. So with this you should be able to tell whether it's a myth or reality if I give you a certain set of statements. AI is constantly learning and improving on its own. That's not true. There has to be a set of engineers who are looking at the performance of AI and they basically gather more data and then retrain and release version 2 or version 3 of that AI engine, or so it's not self learning and improving on its own. So in some cases it can be, I mean there's something called online learning or ever learning machines, but it can be dangerous in many situations because when we learn on new data, the model can forget its how to perform on the previous data. Although we can automate the learning to some extent, it's not exactly like this that it is always learning and improving on its own. AI can be self-aware. As of now it is not true, it's a myth. AI is basically just like I showed you, it's a mathematical function in which you plug in the inputs and it gives you an output. It is not aware of itself, it's just a computer doing basically computing the output of that formula. One needs large investments to get started in AI. That is also not true. There are lots of free resources available, even online computing resources available to get started in AI. And AI is you don't need to be like top of your class to learn AI. Anyone who spends enough time, the mathematics behind it is not very complicated. Just if you know linear algebra, calculus, and probability, then you can get started in AI, and little bit of computer programming, of course. AI will replace only mundane jobs. That is also not true. It is actually coming more and more into more high functioning jobs also. So for example, document search for legal cases and even generating new music and so forth. AI will completely replace humans in most jobs. That's also not completely true. There has to be now the job of humans will shift from doing the job to actually monitoring AI tools do the job and help the AI tools become better and probe the ethical dimensions of using AI and giving the human touch for several services and so forth. AI cannot be fooled easily is also not true. There is a vibrant research going on how to fool AI and how to build more robust AI that doesn't get fooled very easily. AI can make sense of messy data is also a myth. Currently, the models that we have, the frameworks that we have for AI require input to be in a certain format. Only then they can make useful predictions. AI can predict anything with very high accuracy. That is also a myth. Like I mentioned, the underlying model has to be complex, yet it has to be, if it is stationary and it is there actually is a relation between the input and output, then only AI will be able to make a useful prediction. So the key takeaways from this are the following: that machine learning is not a silver bullet. Many times simple models are good enough. And it cannot work with ambiguous, general and unstructured scenarios. When you want explanations, then ML is not able to give good explanations, although it may be able to make good predictions. So our best bet while using ML is to make sure that we have provenance of data, that we know where the data is coming from, both for training as well as validation. We do rigorous validation and we do monitoring of ML models once they are deployed. But ML is definitely useful in many scenarios. It can even go beyond human level capabilities on well-defined tasks. And data is basically the currency of machine learning. The data has to be relevant, it has to be clean, and it has to be realistic for the scenario on which it will be deployed. And basically whenever we have an ML model and its performance, we should critically design and accept or question the ML models before we accept them for deployment. So these are some of the key takeaways. Thank you. I hope you will enjoy this.